So I'm recording to the cloud. How many people are there, do we know? There are 30.
30.
How about the...
Hi, Heracles.
Hi, Bhaskar. So we have somebody from India to San Diego. This is very impressive, no?
Yeah.
It's hard to do better. I mean, very good. Very good. So,
in fact, there are two from India. There should be Debashish also.
And Raghav.
33.
Yes. I'm here.
he's there in a purple outfit.
Very intercontinental.
Yes, very. I mean,
couldn't hope for more.
Okay, so
as get an Australian.
Say a few things, and then we started this initiative. That's the first meeting. We are delighted at the number of people, all of you coming. The organizers are from all over, starting further west with Philipp, who is also the speaker today. Then from England, it's the local Warwick team, which is Kostas, then the Sinem, and myself, and also Agustin Trocoli, who is the master of ceremonies. He's helping us. He's the assistant. He's the graduate assistant for this series. And if it wasn't for him, I don't know how much we would be doing. And of course, now, and then there is Olivier Gosner from Paris. There is Felix from Zurich. And there is Dejo Sale from Bonn. I suppose everybody's here. We are going to record the meetings. We thought there was a problem, but apparently it's only German students who pose problems. Since this is not a student, this is not a lecture for the university, there is no problem from Dejo's side. So, well, of course, we'll ask the speaker every time, and if that's okay, we will record it. Also, we'll try to post the papers or the slides or whatever. It may come in different formats, either the paper if the author sends it or a link. But it would be good when we have the list of back seminars to have also access both to the recording and the some sort of text if people want to look at. There is, of course, I mean, none of us, at least I don't have any experience in running a large meeting on Zoom. And the obvious question has to do with questions. And we agreed, I mean, and Philipp took the risk, which I think is great, that we ran the first meeting with nobody muted. I'm sorry, everybody's muted to start with, but everybody can unmute themselves and ask a question. And if it gets too unruly, then Kostas, who will chair today's meeting, will intervene and restore order so that the seminar can continue. As Kostas said, we plan to start every meeting 10 or so minutes early so that people can say hello to each other, gossip, do whatever. And we plan to go up starting at 3. We plan to go for an hour and with questions throughout. If it goes longer, even better. So that's the plan. Let's see how it works. I have speakers down the road. There is Jakub Steiner, who's somewhere here, who will talk next week. And the third speaker will be Mira Frick from Yale. So we already have 3 speakers. And we're talking to other people, and we'll try to announce the list with enough advance so that people can be convinced to attend. I mean, we'll send every week. The meetings are on Wednesday. We start at so on Monday or Tuesday. We'll send a reminder for the following Wednesday, and also a preview of what's happening the week after. So that's about it. If you have any questions, write to any of us, or there is a website which we try to. I mean, Agustin managed the impossible. He learned Google Sites and made up the website in one go, and it was very impressive. So there may be a problem that you may want to warn colleagues or people that you talk to the seminar about, talk to about the seminar, that okay, I hope this only happens to Warwick people, that messages go to spam. I don't know if it's because from Warwick to Warwick or whatever it is. I did hear people from other institutions complain about spam, unless you had the same experience. If not, we can ignore it and go on. So that's it. Welcome to all. Now, Kostas is going to become host, and Philip, if I know how to do it, make host. So I'm relinquishing change host. So Kostas Kavunidis from Athens now will host, and that's it. Costa.
Okay, welcome everybody. I'm very happy to see so many people and so many familiar faces. Just a few things. We expect the series to run for the duration of the summer, and then depending on how we feel about things, and we may continue it into the fall. After all, a lot of departments may be canceling their weekly seminars, so that could work for a lot of folks. The format is going to be, we're going to open the Zoom meeting a few minutes early, 10, 15 minutes early for small talk. Then there's going to be a 1-hour talk by the speaker. And then 15 minutes are allocated for questions after that, although you may interrupt the duration as well. And then people can stick around and chat. We're not going to close it immediately after. Heracles went over the rules for the questions. One more thing, our website. I want to post it in the chat. In case you haven't subscribed, you can subscribe for emails that are going to reveal to you the Zoom links of each meeting. They go out on Tuesday. And it'll also have the papers of previous speakers and future speakers, the schedule, and direct people there who want to receive our emails and sign up for the seminar. All right.
Okay, so there is a request. Am I muted?
No, you're not.
Okay. So there is a request from, apparently the spam problem also occurs in Glasgow. I don't know.
Well,
but,
we're sending everything
now,
through MailChimp. This is an institutional issue.
I don't think it's more widespread than that. Now, Olivier is asking whether the speaker, Philipp, can share the slides because he wants to take notes.
Yes, of course. How do I do this?
Too good a student. I have no idea.
In the chat, I think. In the chat, you can add a file.
Yes, in the future, we'll try to have the slides as well as the paper posted on the website so you can follow.
But no, because the thing is that you don't want to ask people to, they may not send you the slides ahead. Okay, you understand what I'm saying. We'll see. So if it can be done, or Philip, don't spend too much time. If it's not easy, email the slides to Kostas or me, and we'll try to get them over to Olivier, okay? Oh, it's already here.
Yeah, so yeah, very good. Very efficient. With this, all right, I want to welcome Philipp Strack to talk to us about extreme points in majorization, economic applications. He's our first speaker. We're very happy to have him here. He's from Yale University. And Philipp, you have roughly an hour, including questions, and then you'll receive additional questions at the end. Take it away, and thank you.
Can you hear me?
Yeah.
No.
Oh, perfect. But there's this green thing. Do you see this green box on the screen for you?
We see your slide.
Well, okay. We see the green box, but we don't know what to do about it.
Okay, I don't know what to do about it either. Let me try this. Okay, there will be a green box. I don't know where it's coming from. I'm sorry for that. Okay, most importantly, the paper is joined with Andreas Kleiner and Benny Moldovano. What is the paper about? We are thinking, isn't this green box very annoying? Let me maybe close this and try again.
I did not find the green box very annoying.
No, we should not.
This Peter.
Okay, perfect. So doing it again solved it. So, so what we think about in the paper is, so there's a broad range of economic problems people have been thinking about in theory and related fields. For example, auction design, where you decide how to allocate objects and design transfers. Information design, where you think about what information to reveal to a receiver in Bayesian persuasion problems in order to influence the action they take. Or optimal delegation, where you have an informed receiver and you design the set from which this receiver can choose an action, decision making under uncertainty in semantic decision theory or in finance portfolio optimization. And these problems seem all very different. And the first observation we make is that all of these problems have a common mathematical structure. And I think this is not obvious, and I will explain, going through these applications, how to arrive at that conclusion. But all these problems can be rewritten as a maximization problem over functions which are subject to a monotonicity constraint. So these functions need to be non-decreasing, and a majorization constraint. For example, in the auction context, the monotonicity constraint corresponds to incentive compatibility, and the majorization constraint corresponds to interim feasibility or the border constraint.
Is it smart to ask about masking Nash implementation? You have something similar, or am I missing the point?
I think this will become clear a little later, if you give me a little bit of time. But it would be nice to ask questions. But I think
okay, let's go. Sorry,
we'll go there a little later. Okay, so all these, so something we uncover is that all these problems share a common mathematical structure. And so what we will do in the paper is we will do three things. So we will study this mathematical structure, and we will characterize the extreme points of sets of non-decreasing functions that are either majorized or themselves majorize a given non-decreasing function. And then we will provide tools to optimize over this set. And these tools will be useful because, as I told you in the first slide, all these various economic problems can be rewritten as an optimization problem over such a set. And then we will show that you can actually get new insights in a number of these economic applications from that perspective. It's in some sense a unifying approach which tells you all these problems are the same and provides you with some new insights into these problems. So some new results we get, I mean, we recover old results with very little work, but we also get some new results. So we will provide a characterization of an optimal persuasion mechanism. We will characterize optimal delegation mechanisms, allowing for stochastic mechanisms. We will show a quite general equivalence between persuasion and delegation. And we will generalize Border's theorem on feasible auctions, which is a classical result in mechanism design. And so it's a little bit hard maybe to understand these precise results. I will try to go through a few of them in the talk, but probably won't manage to go through all of them. So the talk is a little bit difficult to give, I think, because it has this mathematical part, and then it has these applications. What I will try throughout the talk is to present a few mathematical results and then show a little bit of application and then go back to mathematical results to make it maybe more interesting. And yeah, please ask questions at any point when something is unclear. Okay, so let me first introduce the mathematical structure we are thinking about. So throughout the talk, we are only going to consider non-decreasing functions. and these functions should be integrable. And majorization, as it was defined by Hardy, Littlewood, and Polya, says that if a function f majorizes g, which we will denote by g and this curly inequality sign, then the integral from x to 1 of g is less than the integral from x to 1 of f for all x in 0, 1. So that is the definition of majorization. So you can see this visualized in the picture, where the blue line is first above the red line and then below. So, and when we say something majorizes this, we also impose that for x equal to 1, equality holds. This is in some sense a familiar object. If f and g are cumulative distribution functions, then this is exactly equivalent to mean preserving spreads. So we would stay in the language of majorization, but you could think of these as distributions as being mean preserving spreads. But because we don't apply it only to distribution functions, and a lot of these original results we're using are cast around majorization, we will throughout talk about majorization, but you can always think about these as results on mean preserving spreads. Just to recall, a mean preserving spread is equivalent to second order stochastic dominance plus equal means. So this is something. Okay. And what we want to study are sets of the following form, or where we fix a function f, and we are interested in all non-decreasing functions g that are majorized by f, or vice versa. So this defines a set of functions. You take all the functions who are non-decreasing and are either majorized by f or themselves majorize f. These sets have been studied in the mathematical literature without the monotonicity constraint. So if you take all functions, not only the monotone ones, then there's 2 papers by Riff which actually characterize these sets. So the mathematical contribution here is to add this monotonicity constraint, which actually substantially changes the nature of these sets. It's immediate to see that these sets are convex because the constraints are linear, so they are preserved. An extreme point of a convex set is an element x that cannot be represented as a convex combination of 2 distinct elements. So in this little picture here, if this is the set A, the extreme points are the marked blue points, because these are the points which cannot be represented as convex combinations of 2 other points. So what we will be interested in is understanding the extreme points of these convex sets of non-decreasing functions which relate to some given functions through majorization. And you could ask, why are we interested in this? And there are 2 results which tell you why understanding these objects is useful. The first is Bauer's maximum principle, which tells you that under some regularity condition, every function which is maximized over such a set, over a convex set, attains a maximum at an extreme point. So once you understand the extreme points of a set, you can, in some sense, without loss of generality, restrict to them in the sense that you will find a maximizer on the set of a convex function on the set of extreme points. So this will simplify your maximization problem and tell you something about the structure of maximizers. So in economics, we're often interested in the structure of the optimal policy. This will correspond to the structure of the extreme points of these functions. The second result, which tells you why extreme points are important, is the Krein-Milnard theorem. And it tells you that every set, in some sense, is described by its extreme points, in the sense that under some technical condition, the set is the convex hull of its extreme points. That doesn't mean necessarily that every point can be represented as a convex sum of extreme points, but it can be at least approximated as a convex sum of the extreme points. In finite dimensions, in fact, every point can be represented as a convex combination of the extreme points. What this implies is that every property that holds true on the extreme points holds true on the whole set if this property is preserved under linear transformations. And that turns out to be a very powerful tool in proofs, and I will use it at several points. So let me first introduce these sets a little bit more formally. So we are interested in the sets omega m of f, which is the set of all non-decreasing functions which are majorized by f. In the mathematical literature, this has been called the orbit or monotonic orbit of f. And we are interested in phi m, which is the opposite. It's all functions g, which themselves majorize some given f and are non-decreasing. And we impose two conditions to make this set compact. We just bound the range of G to ensure compactness. And so the first proposition, which is really, half of it is Choquet's theorem. So it says that these sets are convex, that's immediate. They're compact in the L1 norm, that's not completely immediate. And for every point in these sets, there exists a probability measure over the extreme points, which has support equal to the extreme points, such that the point G can be represented as the average over these extreme points according to the probability measure. And so this is Choquet's theorem, and that's extremely useful. This tells you that every function in this set you can represent as a randomization over the extreme points. And so let me give you our main result. And the result is as follows. So consider a function g, which is an extreme point of omega m of f. It is such an extreme point if and only if there exists a collection of intervals such that outside these intervals, which we denote by I, the function g is equal to the function f, and inside each interval, it's equal to the average inside that interval. So either it's equal to the original function in this picture, so f is the diagonal here, so g is either equal to the original function, or it's equal to the average inside the interval. So the only thing you can do to go from f to an extreme point of the set of functions which are majorized by f is to pick a countable collection of intervals. So these might be infinitely many. And in each interval, replace f by its average. If you take the interpretation that f and g are cumulative distribution functions, then these jumps here corresponds to mass points of the distribution. So what this operation here is doing is it's pushing the mass which is inside the interval outside on these endpoints of the interval. The probability mass, if you interpret these as cumulative distribution functions. We get a slightly more complicated characterization of the extreme points for the anti-orbit of f, which is, again, there's a countable collection of intervals. And within each interval, there's a subinterval which might or might not be empty, which we denote by y lower bar I, y upper bar I, such that outside these large intervals, it's equal to f. And inside these intervals, there's two possibilities. Either you put a mass point, a single mass point inside, if you take the CDF interpretation. So the new function is constant equal to the minimum, and then it makes a jump, and then it's equal to the maximum, while exactly preserving the mean inside the interval. Or there are two jumps, which again need to satisfy the condition that they preserve the mean. But you can only have one or two jumps inside for any extreme point. And so these results are proven through perturbation arguments, where we essentially argue that if you have something which doesn't have this structure, there exists a perturbation such that you can represent these points as convex sums. So the proof is very direct. Let me not go into the proof so much, but let me explain to you why these results might be useful, which I think will also help to understand these results better once you see them in applications. Any questions so far? Okay, so let me apply this to an auction model and tell you how this can be useful in an auction model. So this is a relatively standard auction model. So there are n agents. Each agent's type is distributed on 0, 1 according to some cumulative distribution function f, which has some bounded density little f, which is greater than 0. And there are n objects, and these objects have quality quality q1 to qn, and without loss we are assuming that there are only n objects. This is without loss because if you have more than n objects, you can just dispose the worst objects. If you have fewer, you can just add objects with 0 quality. So without a loss of generality, there's just n of them, and each agent just wants 1 object at most. So if an agent I with type theta I receives an object of quality qm and pays t for this object, then her utility is given by theta I times qm minus t. So it's a completely standard auction model. And we denote by capital pi the set of doubly stochastic matrices, which will be random allocation over objects we give to these agents. And so an allocation rule is a mapping which takes as an input the vector of types of these agents and then spills out an allocation rule, how these objects are potentially randomly allocated among agents. So in this single object case, it just tells you what is the probability of each agent to get the object. Okay, so we denote by A star the assortative allocation rule, which is just that the person who has the highest value gets the highest quality object and so on. Now, what we define is we define the expected quality an agent of type theta I gets in a mechanism. And so this is just the allocation rule times the quality vector integrated over the expectation of other types. So for agent I, you take the expectation with respect to the types of agents other than I, and so this defines the expected quality of the object agent I gets if her type is theta I. So this is the interim allocation rule, and the object, for example, is studied by border. It will be a little bit more convenient to have this in terms of quantiles, so we just redefine these objects in terms of quantiles of the agent's types. And now a theorem is the following. A symmetric monotone interim allocation rule is feasible if and only if it's majorized by the efficient allocation. So the set of interim allocation rules which are feasible is completely characterized by a majorization constraint relative to the efficient or assortative allocation rule. Furthermore, for any symmetric base incentive compatible mechanism, there exists an equivalent mechanism which is in dominant strategies, which gives every agent the same interim utility and creates the same social surplus. So these are two celebrated results or generalizations of two celebrated results from the auction theory literature. So the first one is a result by border, but other people have worked on it before. The version most related to this result is for n identical objects has been proven by Yang Kuche and co-authors. And the second part, the equivalence of Bayesian and dominant strategy incentive compatible mechanisms has been proven, I think, first by Manelli and Vincent for a single object, and then in a very general context by a paper by Alex Gershkov and co-authors. Let me show you how to prove this with the tools we developed in essentially no work. Okay. So these results, if you look at these proofs, they're actually serious work, and this is a generalization of these results, at least restricting to symmetry in part. Let me give you the proof. So the first observation is that the fact that every interim allocation rule is majorized by the efficient interim allocation rule follows essentially immediately from the fact that the assortative or efficient allocation rule maximizes the expected quality given to high types. So if you go back to the majorization constraint, this object here will, if you just plug in this phi function, it will be the expected quality given to a type higher than x. And it's immediate that the assortative allocation rule maximizes the expected quality given to high types uniformly across types. So the necessity of this condition is immediate. So the hard direction is that this is sufficient, and let me prove also that this is sufficient. So let us first not look at the whole set of interim allocation rules which satisfy this condition, but let us only look at the extreme points. The extreme points are exactly the functions where, if you recall here, either it's equal to the original function, which here is the allocation in the assortative mechanism, or it is a flat part where something is replaced by an average. So the only thing I need to do is either implement the assortative allocation or replace it by its average. Well, how could I do replacement by average? So the only thing I have to worry about now is how can I go from the assortative allocation to replacing it by an average inside an interval. Well, that's very easy to do. You just take the types in an interval, and then either you re-randomize these types or you do random serial dictatorship among all the types who realize in an interval to allocate the objects. And that will, in fact, because you give every type exactly the same allocation, and you just allocate whatever the set of types in that interval should have gotten, replace it by an average. So this averaging operation corresponds to replacing whatever you have been doing by applying a random serial dictatorship on that subset of agents. So every extreme point is implemented by either allocating assortatively, or for these types where you need pooling, just treat them the same in your favorite way. So that's actually a very easy mechanism which implements every extreme point. So now, and one observation here is that every extreme point, this can clearly be done in dominant strategies because you can implement the assortative allocation in dominant strategies. So now you need to go from extreme points to the whole set. Well, how can you do that? You just make the observation that by our first proposition and essentially Choquet's theorem, we can represent every point as a randomization over extreme points. So that immediately tells you how to implement every other point. The planner or the designer just randomizes over these mechanisms according to the probability measure that you get from this representation theorem. So this also tells you that you can implement every feasible allocation in essentially is by randomizing over mechanisms where you pool agents in intervals and then do the assortative allocation. And you just pick the intervals where you pool randomly. There's some caveat here that the majorization constraint was weak, which corresponds to setting the allocation to 0 below some threshold, which you can easily do by introducing a reserve price. Note that these results are usually quite a lot of work to prove, and from this majorization perspective on the problem, you more or less get them immediately. And the methodological part here is that if you want to prove something about the sets of this type, you can just focus on the extreme points and establish the property on the extreme points. And if these properties are maintained under randomization, which dominant strategy incentive compatibility, for example, is, then you can lift the property by just proving it on this very small set of extreme points, where you just need very few mechanisms to the whole sets of all these functions. Any questions?
How much work is left from now if you want to characterize completely the solution? If I understand correctly, you're in the class of random mechanisms. So if you wanted to have something in non-stochastic mechanisms, there would still be some work left to do, right?
Yes, but actually our characterization tells you immediately what that is. So something I didn't tell you is in the paper we actually prove that all extreme points are exposed. What that means is that every extreme point is a maximizer of a linear functional. So whenever your objective is convex, and the typical objectives in mechanism design are expected values which are linear, then they exist a maximizer at an extreme point. So you can, without loss of generality, not do this randomization over intervals. But what you will need to do is fixing these intervals to random serial dictatorship. So you can never go around that. So they exist a linear objective, which is some problem where each of these extreme points is optimal. So this is an exact characterization of the things which could appear potentially in some problem. And I will give you conditions which further characterize this a little bit later in the talk. But this is a complete characterization in the sense that for each of these extreme points, there exists one problem where this extreme point is uniquely optimal. This is something we prove in the paper I didn't show you. So there's no further structure you can infer without making further assumptions here. Heracles, you're muted.
What do you say about every extreme point?
So every extreme point is exposed. This is something we prove in the paper, which means that there exists a linear functional, which you can just think of as an expected value, such that the extreme point is the unique maximizer of that functional over the set omega m.
Okay.
So you cannot rule out any of these extreme points a priori. Huh? Okay. So a functional L, sorry.
There's a question in the chat.
Oh, I don't see the chat.
So it says should I read the question? Yeah. In what way is your result a generalization of existing results? I don't remember those results, so perhaps would help me to understand your result.
Okay, so so I guess this question is about the application to auctions. So first, the extreme points of this set have not been characterized before. So the closest result I know of is the characterization of the set of the orbit without the monotonicity constraint. So I don't want to claim that these are major generalizations of results which are known, which are not known. So here the paper by Yanko Chi I mentioned already has a characterization of this type. So they use network theory to obtain a characterization which is very general, and then they specialize to the case with n identical objects and give a characterization of feasibility in terms of n identical objects using these network flow arguments. Note that their condition looks very different because it's not expressed in terms of majorization. So in another paper with Alex Gershkov, Benny, and Mengxi Zhang, we re-express the conditions from their paper in terms of majorization for n identical objects. The difference here is we don't assume the objects are identical. But I don't want to claim that this is it's not the point here that this does any major generalization because the objects are non-identical. The point here is that the proof is really very, very easy, and you really understand the structure of the problem. What I want to advertise here, and hopefully convince you of, that this is the right structure to think about the problem to easily characterize this set. For the second part of the question, this equivalence between DIC and BIC mechanism, this has been known much more general than this result. it is a much more general result in this paper by Alex Gershkov and co-authors. So we are not providing any generalization here. We're just able to prove it for the symmetric case very easily.
So Peter Hammond here, this question may be naive, but so somewhere you had transfers and a quasi-linear utility function. So these striking and interesting results. So the transfers are somehow in the background, ensuring the incentive constraints are satisfied. Is that how it works?
Yes. So we know that all monotone functions can be implemented under these conditions. So this is why we are interested in characterizing monotone functions. So in this theorem, we looked at monotonic interim allocation rules because we know that the incentive constraints corresponds to monotonicity in this setup.
Great.
Know that these tools are useful in another paper, which I just mentioned by Benny, Alex, and Meng-Si. We use this to solve mechanism design with investments before the auction in I think much more general context than it has been done before. And we are able to do this using tools which are tools from majorization. So I think these results are useful. Maybe let me progress a little bit because I have quite many applications and maybe
I'm sorry, Olivier, I have a question. You lost me at some point where I thought you were working in R in intervals, and all of a sudden this allocation problem is in Rn. And
yes.
So there is something magic that happened, or I just lost everything.
So the symmetry is the magic thing. There's nothing magically here. I just a priori restricted to symmetric mechanisms.
Okay. So that's cheating, really, no?
So first,
I mean, like,
first you can do this. It is reducing the problem. I don't know if it's cheating. Actually, you can use these tools in the non-symmetric case. It's just much more complicated. What I wanted to give here is you an illustration on how you can use these tools.
Right, but can you generalize your tools to Rn? That's maybe a better question to ask.
So let me. No, I think the multidimensional majorization problem in Rn is really hard. But you don't need to prove. We conjecture you don't need to prove these types of results. So this specific result for more than without the symmetry restriction.
Thank you.
This really goes beyond what I want to explain here.
Thank you.
Okay. Let me now. So this was just an illustration how the general result is useful. Now let me get back to Deje's question. How can you find which extreme point is optimal if you're looking at a concrete problem? So a functional V is sure convex if it respects the majorization order. And now you could ask what functionals are sure convex for the case of linear functionals in F. There is a characterization theorem by Van Lorentz, which is extremely useful. And so this theorem tells you that if your objective is the integral over some function k, which depends on f and t, then it's sure convex, so monotone in majorization, if and only if this function k, over which you take the integral, is convex in U, which is the first component, and supermodular in the combination of the two components. So that's necessary and sufficient. This result doesn't require any differentiability, but if you're willing to impose differentiability in addition, this becomes a very, very simple condition on the derivatives. Yeah, so it's a very easy to check condition. Let me try to illustrate this by connecting it to a classical result in decision theory. So think of rank-dependent utility functions, which are utilities where you do not only distort the outcome as an expected utility, but you also distort the probabilities according to some function g. These generalize, for example, for Neumann-Morgenstern expected utility, but also Yaris dual utility. A classical question in this context is, when is such an agent risk averse? So for expected utility, you know that the agent is risk averse if V is concave. Actually, in Yaris preferences, the same holds true. G needs to be concave for risk aversion. For this general domain, it's not so obvious. So very classical result in decision theory is that this is the case if and only if the V and G are both concave. How does this relate to what I just told you? Well, I told you initially that majorization is equivalent to mean preserving spreads. So risk aversion is monotonicity with respect to mean preserving spreads. That's the definition of risk aversion. So you're essentially asking the question, when is this functional monotone with respect to mean to more majorization, which is sure convexity? So the previous theorem tells you the answer, and you just actually need to differentiate this function to prove this result. It's immediate, it's a one-liner. But in the original proof of these results, there went quite a lot of work. But so this perspective really makes these results more or less immediate. So you can now use this. This is just an illustration also how this connects to decision theory. Let me now zoom in a little bit more and think about how to maximize concrete functions. And so in most of economics, we actually don't deal with general convex functions, but with linear functionals. So let's focus for a moment on linear functionals. So suppose you have some linear functional where you want to maximize c times h of x, where h is h is chosen from the orbit of monotone orbit of f. A lot of problems, like the auction theory problem I've just shown you, under the restriction to symmetric mechanisms, can be written in exactly this form. And so now, if c is non-decreasing, then f itself is the solution to the optimization problem. This corresponds to the case, so c is in the auction problem the virtual value, so this gives the result of Meyerson without the I-ring. If c is non-increasing, then the solution is a constant function, just equal to the average. And if c is non-monotonic, then the other extreme points might be optimal, where you kind of flatten out these parts. And this exactly corresponds to Meyerson's ironing procedure. So these other extreme points are exactly the equivalent of what happens in Meyerson's problem when you iron out parts. And in the paper, we describe this ironing procedure. It needs to be a little bit generalized to work in this more general context, but we describe how to do that in the paper. So let me maybe very briefly talk about matching. And so this is an application to matching context where there are prices and agents. Agents can exert costly effort, and one way of matching them is based on the agent who exerted the most costly effort gets the highest object. And again, you can define the assortative matching, where you just do this assortatively. And this matching is good because high types will get good objects or high prices, which if the utility is multiplicative is good, but it's quite bad in the sense that a lot of wasteful effort is exerted. And you can think about other matching themes, for example, just allocating the objects completely randomly, ignoring the effort done by agents, and there's a literature discussing these things. Here, these matchings are in fact also described by a majorization constraint, and you can get you can exploit this very similar structure, similar to the auction, and define the utility of an agent and the overall welfare. And a characterization of these matchings is that an allocation rule in these matchings is feasible and implementable if and only if the induced distribution of prices, the inverse of that, satisfies a majorization constraint. Now you can immediately use these results from van Lorentz and see that if the distribution of types is convex, actually the van Lorentz condition, the inverse van Lorentz condition is satisfied, and you get like a flat matching is optimal. If f is has increasing failure rate, the opposite happens, and you can apply van Lorentz condition, and if you have decreasing failure rate, the assortative matching becomes optimal. Essentially, it becomes immediate to characterize under what conditions on the distribution of types, what type of matching schemes maximize welfare. Okay, let me now go a little bit to the anti-orbit, which is the opposite majorization condition. So it's all functions G that majorize F. And again, if C is non-increasing, then the original function solves the problem. That follows from Lorentz. If C is non-decreasing, then you can obtain the optimum at a step function, which is the extreme points where you take the whole interval, and otherwise other extreme points are optimal, and you need a actually quite different ironing procedure, which we describe in the paper. Let me briefly apply this to Bayesian persuasion. So suppose there's a state of the world which is distributed on 0, 1 according to some prior. There's a sender who chooses a signal which reveals some information. So that's a Blackwell signal which reveals some information about the state of the world. And every signal introduces a distribution over posterior means. And suppose the receiver observes the choice of the signal. So as in a Bayesian persuasion problem, he knows the Blackwell information structure which is chosen. And then after seeing the signal realization, chooses an optimal action. And let's assume then the receiver's preferences and sender's preferences depend only on the posterior mean. That's a common setup analyzed in various papers, which I mentioned on the top of the slide. You could ask, so how does this relate to our problem? So here it's immediate that Blackwell monotonicity corresponds to mean preserving spreads. And mean preserving spreads, as I mentioned initially, correspond to majorization. So here it's really immediate that there's a characterization of this problem in terms of majorization, because Blackwell monotonicity is just majorization. It's exactly the same condition. So the sender's problem becomes to choose a CDFG out of the anti-orbit of F, maximizing the interim utility V of X. So this problem is also within this framework where you maximize over some set of monotonic functions related by majorization to a given function. Our result now tells us that without loss of generality, every such problem, the solution, there is a maximizer at an extreme point. So different types of signals could be optimal. So remember, we had two types of extreme points. One where there was a single jump, and one where there were two jumps. So the literature is called the first one monotone partitional signal, where there's just a single jump in the middle of the interval, which corresponds to a mass point. So there's a single signal you send in there. And the other type of extreme points we characterize where you use two extreme points. So the theorem which follows immediately from this is that there exists an optimal signal structure for any of these problems, which has the form that either it reveals the state perfectly, or it pools all states in an interval into a single signal, or it sends two different signals in an interval, but never more than two. This is an immediate conclusion from the extreme point characterization. And this has not been known until recently. And independently at the same time, this characterization has been obtained in a paper by Ariely et al. And there's an earlier paper which I just found out about by Kandogan, where under additional restrictions, a partial part of this characterization is obtained. But so this has not been known before. It follows immediately from the extreme point characterization. And it tells you that really, if you want to solve such a Bayesian persuasion problem, you never need to use more than two signals. So you just pick a collection of intervals, and in each interval you either send one or two signals, but never more. And so this drastically simplifies the space of policies over which you have to search for an optimal policy.
Philipp?
Yes.
This is Ran speaking. Let me just mention, as a co-author of the paper for Ariely et al., it's miraculous that it's not only the same result, but the same technique. That's one of these miracles where people independently at the same time do the same thing.
Yes.
It's the same extreme point technique.
That's nice. Yeah, well, one point here is also that actually what we didn't prove first, and what you prove in your paper, is that these extreme points are exposed. So I didn't talk about exposedness here. Okay, good. So let me go to another application, which I think this is the application where we make the most progress in terms of novelty of results. Which is, suppose there is a state of the world which is distributed on some interval, and this state realization is observed privately by an agent, and there's a set of possible actions, and there's an agent and a principal, and both of them have quadratic loss utility, and but the agent and the principal have a different most preferred point which they want to choose depending on the state. And so the agent privately knows the state, and the principal doesn't. And now you could ask, what type of mechanisms can you use where the agent reports the state to the principal, and then the principal takes a decision? A very simple mechanism is a delegation mechanism, where the principal just chooses a set of actions the agent can choose from. But more generally, you could think about random mechanisms where you assign to actions, where you assign to reported states distributions over actions. Yeah. So, for example, if you allow the agent to choose from the set theta lower bar, theta upper bar, then the states above theta upper bar, the agent will just choose the action theta upper bar, because that's the closest he can get to his most preferred state. And below theta lower bar, he will choose the action theta lower bar, and that will give you the blue curve. Something which is implementable here is you can further restrict the agent and make this set smaller, so that above some intermediate point, he chooses the action. So you don't allow the actions between theta star and theta upper bar, and then the agent will choose whatever is closer, either theta star or theta upper bar. But you can also implement things which are not related by majorization here. And so, for example, the green line is not related to the blue line in terms of majorization, but it still corresponds to a policy. So in this setup, because here if you just above some point theta star do not allow the agent to choose any policy, this will not be related with respect to majorization to the blue policy. So it's not immediate, and it has not been known before that this setup can be also related to majorization, and you can do this by a technique which has been proposed before, by expanding the state space. And so the action space and state space, and so you just can make the state space sufficiently large, and then you recover a majorization relation on that kind of virtual state and action space. Let me not go into too much detail here. Let me just give you the result. So suppose you you describe a mechanism in terms of the mean chosen by the principal as a function of the reported state and by the variance. These are the only two objects which matter given the mean variance preferences we assumed. Then you can re-express the preferences of the agent and the principal only in terms of these two objects. So these are a complete description of mechanisms. And now you can ask which of these mechanisms can be implemented. And so the first thing we do is we restrict to a subset of mechanisms. And the subset we restrict to is these mechanisms which we call undominated, where the set of actions which are, so there doesn't exist another mechanism where the action is, there's just a unique action that is better for the principal. Like the principal can always pick an action directly, ignore all reports, and we only restrict to those mechanisms which are not dominated from the principal's point of view by such a mechanism. This subset of mechanisms can be characterized in terms of majorization. And so this is the lemma and the new characterization of these delegation mechanisms. So an undominated mechanism mu sigma squared is incentive compatible if there exists some extension of the mechanism to a larger interval of types and actions, such that the lowest, when the lowest virtual type realizes, you get the lowest action and zero variance, and the same at the highest type. The mean is dominated by the identity function. So that is the mechanism which always allows the agent to choose freely whatever he wants. So we have a majorization relation relative to the function which allows the agent to choose whatever he wants. And the variance chosen is characterized essentially by an envelope condition. So this characterizes the set of delegation mechanisms within this space of anti-orbits. And now, given this characterization, you can apply the von Lorentz theorem to get further insight into the structure of the optimal mechanism. So the first thing to do that is we need to kind of derive a virtual value, and that has been done in the literature before, and we very much follow the recipe for that. And now you have recasted this problem as maximizing this objective VP over this set of anti-orbits. So now what we know from the result is that the extreme points, some of them are deterministic, but some of them involve randomization, which are exactly those extreme points which have two mass points in an interval. And now you can use the tools, and we do that in the paper, to characterize which extreme points are optimal. And yeah, so I think this characterization is noble. It also implies an equivalence between the persuasion problem and the delegation problem. And such an equivalence has been observed before if one restricted to deterministic delegation mechanisms and monotone partitional signals, which are exactly the extreme points where there's just one mass point in each interval. But now this new characterization generalizes this to randomized mechanisms, and Bayesian persuasion and removes the restriction to monotone partitional signals in the context of Bayesian persuasion. And I think this has not been known before that. So the reason these problems are really equivalent is because they share the exact same mathematical structure. So from this perspective, also this equivalence is maybe not entirely surprising. Yes. So I don't know how I'm with time. Let me conclude. So what did we do? So we provided a characterization of extreme points of monotonic functions that are either majorized by some given function or themselves majorize that given function. And this is useful because many well-known problems in economics, many well-known optimization problems can be rephrased as maximization problems over convex functionals over such set. Which implies that if you want to search for a maximizer, you can without loss restrict attention to extreme points of these sets. So once you obtain a characterization of these extreme points, you know that you can look at a much smaller set of functions. And this is useful because then on this smaller set, you might be able to prove properties much more easily. So for example, implementability really became a very easy proof in the context of Border's theorem, because you only needed to implement those allocation rules, which are either assortative or pool agents in an interval. And now it follows from Choquet's integral representation theorem that properties which you can prove on this much smaller set of functions live to the more general space, and this greatly simplifies in establishing properties. And an open question which relates to what Olivier was asking about is how to do this for multivariate majorization. And this is, I mean, there's also an open question even without the monotonicity constraint in mathematics. Like all these questions around multidimensional majorization or the multidimensional convex order are really quite hard, because we don't know how to use the extremal arrays of characterizing these in a helpful way. So we don't know how to do that. Some of the results I've shown you can be actually handled with an extension which doesn't require multidimensional majorization. But yeah, we've been thinking quite a bit about multivariate majorization, and that seems to be a difficult problem.
Thank you. Are there any questions?
So I just have not a question, but I'm repeating what was said by a number of this, you know, this majority. It seems it's like a miraculous unification of a number of results. So, can you give us some more intuition? I mean, you did, but what is it that drives all the results? I mean, it's not.
So I think what
question, but I mean, it's striking that all these different results boil down to the structure.
So I think what's driving is that in all these stochastic orders we've been looking at, mean preserving spreads, the convex order, majorization, Blackwell dominance, all these are the same order. And so a lot of these problems boil down to having a constraint in one of these orders and monotonicity. And
I see.
The striking thing is that essentially all these orders are the same, which they're all mathematically the same. They're economically very differently motivated where they're coming from, but they're all the same order, at least in the single dimensional case. The picture is much more complex in the multidimensional case.
I see. Mm-hmm.
And yeah, so this makes all these problems more or less the same.
Any other questions?
Can I ask something about the equivalence between delegation and persuasion?
Yes.
Does that mean that the optimal form of delegation and the optimal way to provide information induce the same decision functions? So are they equivalent?
Can you repeat the last part of the question? Sorry.
So you say that there's an equivalence between the problems. Is there an equivalence between the solutions? That's what I'd like to know. Is the optimal form of delegation and the optimal way to provide information, do they induce the same choice functions?
So the equivalence is in the sense that if you give me a delegation problem, I can formulate a persuasion problem where the optimal policy can be inferred. So there's a mapping between the solution to one. So if you can solve one problem, you can solve the other. For every persuasion problem, I can formulate an equivalent delegation problem and vice versa. Does it help? Sorry.
Thanks. Yes, that answers that. Thank you.
Any other questions? All right. Well, thank you very much, Philip, and thank you everyone else for showing up.
Thanks a lot.
We know how to upload, we don't, do we?
We're not closing this. So if you want to stick around and chat afterwards, that would be nice. And thanks, everybody.
Thank you.
Thank you.
Thank you.
Heracles, it's very good to see you here.
Yes.
I turned off my video precisely because I was vigorously exercising, which is what I usually do at 7 in the morning.
Okay.
We will be posting the videos if you feel like we're forcing you to wake up at an ungodly hour. Just sleep in and.
Just didn't want to miss my exercise.
I was guessing that you were exercising from the looks of that before you turned your camera off.
I canceled the video after about halfway through, saying you don't want to see this.
So now
You got it right.
Oh, very nice.
Very good. Okay, people, so see you next week.
Thank you, everyone.